If we consider some of the spin and orbital angular momentum contributions to the total magnetic moment of the electron, we can see that the result can be written as follows. M total is the spin magnetic moment plus the orbital magnetic moment, and this is going to give us a total of minus E divided by electron charge divided by twice the electron mass times the orbital contribution, orbital angular momentum, and minus 2 E divided by 2me, twice the mass of the electron, electron charge divided by twice the mass of the electron, spin angular momentum, p theta s. So we can see that we can write the total angular momentum in this form. It is minus g E divided by 2 mass of the electron times the total angular momentum. So this G factor is actually going to measure the relative contribution of the orbit and the spin angular momenta. So P total P theta total is the total angular momentum. So we add the angular momenta, and the factor that appears up front, the term G, is called the Lande splitting factor. So if you have G is equal to 2, this implies you have a spin-only contribution. If the Lande factor is 1, that implies orbit-only contribution. So we can see that the role of G here is it measures the relative contributions of spin and orbital angular momenta. Okay, so we can write it in this form: minus G E divided by twice mass of the electron times the total angular momentum. And we have possibly spin and orbital contribution, whose relative strength is measured by the Lande factor G. Now I want to talk about why we need to abandon this classical model. So let's take a look at what happens if you have a spin magnetic moment ms, which is equal to minus a Bohr magneton, or an orbital magnetic moment mo, which is minus a Bohr magneton. So Bohr magneton, remember, is EH bar divided by twice the mass of the electron. H bar is Planck's constant divided by 2 pi. That is 6.63 10 to minus 34 joule seconds divided by 2 pi. And the electron charge is 1.6 10 to minus 19 coulombs. For the mass of the electron, the rest mass, we can take 9.11 10 to minus 31 kilograms. So putting these values together, you can calculate the Bohr magneton to be 9.27 times 10 to minus 24 ampere meter square. So this is an important number we need to keep in mind. 9.27 10 to minus 24 ampere meter square. That's a Bohr magneton. Now, this spin contribution, spin magnetic moment or orbital magnetic moment. Let's talk about the spin magnetic moment. That was given as minus E omega r squared divided by 2 in our classical calculation. And this is basically, since V is equal to omega r, minus EVR divided by 2. So what is R here for the spin contribution? So go back to the spin model. You can see that R will be the radius of the electron. So now I have a challenge. R is electron radius. What number am I going to use for electron radius? So how do we estimate a classical value for electron radius? The answer is the following. We can use a classical relativistic model. So using a classical relativistic model, we have the electron rest energy, that is mass of the electron times speed of light squared, mc squared, and this is equal to the potential energy of the electron, ke squared divided by radius of the electron, where the radius of the electron you can now find to be 1 over 4 pi epsilon 0 permittivity of free space multiplied by E squared over mass of the electron c squared, which is the rest mass. So if you substitute for the speed of light 3 times 10 to 8 meters per second, mass of the electron is 9.11 10 to minus 31 kilograms, E is 1.6 10 to minus 19 coulombs, epsilon 0 is permittivity of free space, we can plug in its value, or K, which is 1 over 4 pi epsilon 0, is 9 times 10 to 9 it's basically newtons per meter square, coulomb square. So F is equal to K E square over R square. So it's going to be Newton meter square per coulomb square. Okay, so Newton meter square per coulomb square. That is K. So if you plug in these values into this equation, you will find that the radius of the electron comes out to be 2.8 femtometers meters. This is known as lorentz radius of the electron. So that's how we estimate the radius of the electron. It has a rest energy mc square, which is equal to the potential energy ke square over r. And why do I have ke square over r? Remember, in my model I have assumed all the charge is residing at the circumference of the circle. So it's ke square over r is the total potential energy. So 2.8 femtometers is the electron radius that I can estimate here. So we have done this calculation. Now I'm going to substitute this. So let's say that my spin magnetic moment is a bohr magneton, which is minus 9.27 times 10 to 24 minus 24 ampere meter squared, and this must be equal to minus electron charge radius of the electron divided by 2 times the velocity, tangential velocity of the electron. So if you substitute for r 2.8 femtometers and electron charge is 1.610 to minus 19 coulombs, you can calculate the tangential speed of the electron to be 4.1 times 10 to 10 meters per second, which is greater than the speed of light. It's actually 2 orders of magnitude greater than the speed of light. That cannot be. So we conclude that we have an unreasonably high tangential velocity. So we can list a few things that are wrong with that seem to be wrong with this classical model. One of them is unreasonably large tangential velocity. So we cannot have this classical model. The other point is that we're assuming we have a continuous angular momentum. Angular momentum is quantized. And related to this, magnetic moment is quantized. And this is experimentally proven using Stern-Gerlach experiment. Where we have the Zeeman effect giving us a splitting of magnetic atoms. So the end result is that the classical view, the classical Amperian current should be abandoned in favor of a quantum mechanical treatment. So in the next few videos we're going to talk about the quantum mechanical model that is going to explain the magnetic moment of atoms, or the atomic origin of magnetism. Okay, so we talked about the total electronic magnetic moment. It has the spin and orbital contributions. So if we add them up, we get minus E over 2 me p theta O minus 2 E over 2 me p theta S, the spin and orbital angular momenta. We can write the total magnetic moment as minus G E over 2 me p theta total, where this is the total angular momentum of the electron, and the term G is the Landes splitting factor. If G is equal to 2, we have a spin-only contribution. G is equal to 1 orbital-only contribution. And so G is a measure of the relative contribution of orbit and spin, orbital and spin angular momenta of the electron. Now, looking at the classical model, if we look at a measured spin magnetic moment, which is a Bohr magneton, and we compare it with the results of the classical model, a Bohr magneton is EH bar over 2me. Substituting these values, we get 9.27 10 to minus 24 ampere meter square in SI units. So if the classical model holds, we would have a spin magnetic moment, which is minus E omega r squared over 2, or minus EVR over 2, because V is equal to omega r. And here R is the electron radius. And now what do I put for electron radius? I can use a classical relativistic model. Electron rest energy mc square must be equal to its potential energy, Ke square over R. K is Coulomb's constant. So substituting for speed of light, Coulomb's constant, and the mass of the electron, the corresponding values, we find the lorentz radius of the electron, which is 2.8 femtometers. So looking at a spin magnetic moment, a Bohr magneton, and substituting these values, we find that the tangential speed of the electron should be 4.1 10 to 10 meters per second, which is much greater than the speed of light. And therefore, because of this unreasonably large tangential velocity, the quantization of angular momentum and the quantization of magnetic moment, which are not expected in the classical model, we realize that the classical Amperian current view should be abandoned in favor of a quantum mechanical treatment.